Hello everyone, today we are talking about the safe conversion of aromatic amines, a topic that's crucial for many industries. First, what are aromatic amines? Well, they are organic compounds where the amino group is directly attached to an aromatic ring. Here's a simple example of an aromatic amine and some of their properties. And it's worth mentioning that the same bond is hard to break, so it's not easy to remove the amino group. These compounds are totally workhorses. They are key for making synthetic dyes and organic pigments. And most importantly, they are the core of pharmaceutical synthesis, used to make many very useful drugs. But here's a catch. They cannot be used directly. To turn them into useful drugs or materials, we need to replace their amino group with other functional parts. That conversion comes with big problems, covering ecological damage, safety risks, and high costs. So, how do we solve these issues? That's exactly what our research on safe conversion aims to address. Let's dive into the details next.
Now, I would like to introduce three aromatic amine conversion technologies. First, is a traditional centimeter reaction. It is classic but high risk. Uses sodium nitrate to make diazoxide salts and toxic copper salts, needing strict 0 to 5 control. Next is the electrochemical centimeter reaction. It's greener but still relies on diazoxide salts. Watch for electric shock and toxic gases from halogenating agents. Finally, it's the N-nitroamine mediated method, the newest, safest option. No unstable diazoxide salts works at 0 to 70 temperature with few reagents. Suppose one pot synthesis scales to 1 kilogram and has low toxicity byproducts.
Okay, after learning several traditional methods of transformation, now I will introduce a new one, which is created by Zhang Xiaheng, a Chinese researcher in the University of Chinese Academy of Sciences. And you can see in the picture, this is the basic transformation route, but I will not go through it because it's all about chemical mechanisms, and this is the job for scientists, not for chemical engineers. So my focus is more on the safety issues and the reaction conditions. Let's move on to the first part. It's the safety issues. Like Zichen mentioned before, the traditional processes rely on the Sandemel reaction, which inevitably generates diazonium salt intermediates, which is extremely sensitive to shock, friction, and temperature change. It is just like explosive packages. In contrary, the new technology used N-nitroamine as intermediates, which are mild and stable. Deamination is achieved through the release of stable nitrous oxide during the reaction. So we use a more safe reaction, and we no longer need to use high-risk protective gears, like in the picture, explosion-proof walls and remote operation systems. And these systems will cost 6 to 20 times higher than the standard factories. Okay, the second part is about reaction conditions. This reaction is reacted under the milder reaction environment. The traditional diazonium salt synthesis demands strictly low temperature control, like about 0 to 5 degrees Celsius to prevent decomposition, while the new technology proceeds under ambient conditions. And for the another part, we no longer need to use the metallic copper, and it can generate substantial hard-to-treat heavy metal wastewater that pollute the ecosystem and incur high recovery cost. So the new technology requires no metal catalyst, completely eliminating high metal pollution. The last thing I will mention is the simplified reaction flow. The reaction used to be multi-step transformations, but now the team developed a one-part strategy by directly adding multiple raw materials into a single reaction vessel without intermediate separation. So it becomes more convenient. I think it's a little bit of like what northern part of Chinese people eat. Like they put all the ingredients in the pot and they cooked it together. I think Marshall have eaten it a lot, maybe.
The nitroamine mediated direct deamination of aromatic amines enables metal-free one-part conversion of ArNH2 into diverse CX and CC bonds at kilogram scale, bypassing hazardous diazonium intermediates. Within 3 to 5 years, ton-scale continuous flow implementation is projected, driven by 90% weight reduction, 40 to 50% lower cost, and elimination of explosion risk, making it the first truly safe and green replacement for 140-year-old cinema chemistry. There are countless advantages after this improvement was made. The industrial production was experienced significant efficiency improvement. For electronic materials, cleaner synthesis of halides and boronic esters will lower the carbon footprint of OLED intermediates and high-performance polymers by 30 to 50%, supporting next-generation displays and lightweight composites. For global sustainability, full adoption across aromatic amine markets could eliminate around 100,000 tons per year of copper-containing waste and reduce sector CO2 emission by several million tons, directly contributing to reach compliance and net zero targets.